The goal of this lab was to use electromagnetic induction to construct a velocity sensor and subsequently an acceleration sensor. The experiment aimed to measure the average velocity of a falling magnet. The sensor worked by applying Faraday's law of induction. As the magnet fell through the coil, the change in magnetic flux induced a voltage spike, which was recorded on an oscilloscope. The time difference between the peaks allowed velocity calculation, and comparing velocities at two different positions enabled acceleration measurements. Equipment that was used were cylindrical magnets, 12 millimeters diameter, thin copper wire, a plastic tube, retort stand, ruler, oscilloscope. The fundamental principle behind this experiment is Faraday's law of induction, which states that a changing magnetic field induces an electromagnetic force in a conductor, where V is the voltage, E is the electric field, and d phi b over dt is the rate of change of magnetic flux. Magnetic flux measures the total magnetic field passing through a given area and is defined as phi equals BA cos theta, where B is the magnetic field strength, A is the cross-sectional area of the coil, and theta is the angle between the magnetic field and the coil's surface. In this experiment, the magnet moves actually through the coil. As the magnet falls through the coil, the magnetic flux increases. As the magnet approaches, voltage peaks when centered and decreases as it exits, inducing a measurable voltage pulse. Magnetic flux actually slows down the magnet, decreasing the accuracy of the experiment because the induced field opposes the motion of the magnet. A plastic tube was clamped vertically using a retort stand, and a coil of copper wire was wrapped around the tube approximately 50 turns. The coils were connected to the oscilloscope. A cylindrical magnet was dropped through the tube. The oscilloscope recorded the induced voltage pulse as the magnets passed through the coil. The time interval delta t between the peaks of voltage were noted. The distance between the coils delta d was measured using a ruler. The two coils were placed at half a meter distance apart along the tube. The time taken for the magnets to pass through each coil was recorded. The change in velocity delta v and the time intervals delta t between the coils were used to calculate acceleration. A equals delta v times delta t. This acceleration was used to compare to the theoretical value of 9.81 meters per second per second. The calculated acceleration, 9.7 meters per second, which closely aligns with the theoretical value of gravity. But there's a systematic error in this experiment caused by the Lorentz force slowing down the magnet. This could be eliminated in the calculations if the magnet's strength was known. There could also be an error in the measurement of the distance intervals.